Okay, now that we've graphed exponential functions and I've talked to you about how we see exponential growth and exponential decay, we're going to talk about how to write those functions and how to use them in real life. So exponential growth occurs when a quantity increases, and so again, as we move to the right, the value goes up, by the same rate r in each period t. When this happens, the value of the quantity at any given time can be calculated as a function of the rate and the original amount. So again, our exponential growth function has the form of y equals a, where a is our original amount of money that we have, or the original amount of people, and then 1 plus r. Now, why do we do 1 plus r? 1 means I want to keep my original amount, and I'm going to add on a rate. Now, our rate is usually given as a percentage. So if it was 15%, the r would be the percentage written as a decimal. So 50% would turn into 0.15. So really, we take the current decimal and we move it forward 2 places. And then t is our amount of time. So the original value of a painting is $9,000. So this is our A value, our original amount. And the value increases by 7% each year. So 7% is 0.07 as a decimal. Write an exponential growth function to model this situation. Then find the value of the painting in 15 years. So our function y would be equal to our initial amount, 9,000, times 1 plus 0.07 to the t power. So t for time. So really, this becomes y equals 9,000 times 1.07 to the t power. Now we want to find the value of the painting in 15 years. So that's our time. So now we're going to calculate y equals 9,000 times 1.07 to the 15th power. So just like we were calculating before, we do 1.07 to the 15th power. And then I'm going to times that by 9,000. So because some of your decimals are going to be really long, you don't have to show as much work. But it's a good idea for points purposes that you put down that this is 2.759. Now, I don't want you to calculate with the 2.759. I want you to calculate with the original decimal, but I don't expect you to write that whole thing out. So that way I can check to make sure that you know how to use your calculator correctly. And so this becomes 24831.28. And this is our real value. So it started off being valued at $9,000, but because of interest or whatever inflation, the painting now, after 15 years, is worth $24,831.28. Okay, next one. A sculpture is increasing in value at a rate of 8%. So remember, 8% would be 0.08. And its value in 2000, so that's going to be a key for us, was $1,200. So I'm going to write y equals, so I know that it was $1,200. And I know my interest rate, so it's increasing at a rate of 0.08. There we go. Write an exponential growth function. Did that. Let me write this a little bit together. 1,200, 1.08 to the t power. To model the situation. Then find the sculpture's value in 2006. Okay, so what do I put in for t? Do I put in 2006? No. I have to look at how much time has passed between 2000 to 2006. So really, my t is going to be 6. And that's what I'm going to plug in. So y is equal to 1,200 times 1.08 to the 6th power. And so now we're going to calculate 1.08 to the 6th power. Oops. And I get about 1.587. But that's not the number I'm going to use to calculate. I'm going to use the entire decimal that's in my calculator, and I'm going to times that by 1200. Most calculators have an answer button, so once you calculate that, you could do answer times 1200, and it'll use that full decimal amount. So that way you get less error in your answer. And so this is 0.249, and since we're talking about money, we're going to go ahead and round that, and we're going to label it as money. So again, just looking at how those exponential functions can be used. Okay, now a common application of exponential growth is what we call compound interest. So you're going to see this all the time if you ever go to the banks and look at accounts. They'll tell you like how the interest is calculated and how it's compounded. So recall that simple interest is earned or paid only on the principal, but compound interest is interest earned or paid on both the principal and previously earned interest. So if they calculate interest once a year, then if I put $1,000 in it and after 1 year they pay me my interest, so let's say they pay me $100. So now I have $1,100. So now they have to pay me interest on the $1,100. And so by doing that, you actually make more money faster, which is how the banks make a lot of money on loans, is that they'll calculate that interest often so that way they are making more money off of you. So how do we work compound interest? Well, it's a little bit trickier than the interest we talked about before. Now I'm going to highlight this because it's really important that I'm able to find this quickly in my notes. So a compound interest function has the form of P, and P just means the principal amount, which is the same thing as our starting value. And then again, we're going to have the 1 plus, so 1 means I'm taking my original amount and then I'm adding, and this is R divided by N. Now R is our interest rate like it was before, but N is how many times we calculate that interest rate. So an interest rate is usually for a year, but if I'm calculating it every 3 months, I have to break up that interest rate, so let's say it's 0.12, over, if I'm doing it every 3 months, I'm calculating it 4 times a year, which means I'm only doing interest at 3% each time, because I've broken up that 12% over 4 times. And then your time is now going to be multiplied by the N. So if I calculate it 4 times a year, that means I'm calculating interest 4 times for every year. And so that's where I get 4 times, like, let's say 6 years. So it may decrease that interest rate here, but it also increases your time. And so in the long run, the more often that you calculate that interest, the more money you make. So some keywords that you need to know is that annually means that you're calculating it once a year, so N would be 1. Quarterly means 4 times a year, so N is 4. Monthly means 12 times a year, and so N is 12. And T is really just time in years. Okay, so let's look at our first problem. We're going to write a compound interest function, and then we're going to find the balance. So we are starting with $1,200. So y equals $1,200. 1 plus, and we have a rate of 2%. So 0.02. And it's compounded quarterly. So our N is 4. And then this is going to be to the 4t power. So we're going to go ahead and simplify this a little bit. So this is 1,200, and I'm going to do 0.02 divided by 4. So this is really 1.005 to the 4t power. So there's my function. Now I'm going to go ahead and I'm going to calculate that value after 3 years. So I'm going to plug in 3 for t. So this is y equals 1,200, 1.005 to the 4 times 3, which is the 12th power. So now I'm going to calculate 1.005 to the 12th power. And so this is going to give me 1200 times 1.0616, so on and so forth. I'm going to times that by the 1200, which means that I'm really going to end up with $1,274.01. So now let's go ahead and look at the next problem. So $15,000, so y equals 15,000, invested at a rate of 4.8%, so this is 0.048, compounded monthly, so we're doing that 12 times a year, so I divide by 12, but now my time becomes 12t. So now I'm going to take the 0.048, I'm going to divide by 12, so now my new function is y equals 15,000, 1.004 to the 12t power. So now I'm going to go ahead and I'm going to calculate that for 2 years. So y equals 15,000 times 1.004 to the 12 times 2, so 24th power. So 1.004 to the 24th power, and then I times that by 15,000, which gives me a value of $16,508.22. So just by putting your money in the bank at that rate, compounded monthly, you earned $1,000 or $1,500 over 2 years, just by leaving it in the bank. Okay, so next problem. We are investing $1,200. So y equals 1,200 times 1 plus. Now our interest rate is 3.5%, so I move that decimal up 2 spots, 0.035, divided by compounded quarterly. So I'm dividing it by 4, which means my time is now 4t. So I'm going to go ahead and simplify that a little bit. 1,200, 0.035 divided by 4. So 0.00875 to the 4t power. And now I'm going to plug in those 4 years. So this is really y equals 1,200 times 1.00875 to the 4 times 4, 16th power. So I calculate 1.00875 to the 16th power. Then I'll times that by 1,200, which now gives me $1,379.49. Okay, next one. $4,000 invested at a rate of 3%. So y equals $4,000, 1 plus 0.03 divided by 12, because it's compounded monthly. And then monthly is 12, so 12t power. So y equals 4,000, and then 0.03 divided by 12 gives me 1.0025 to the 12t power. So now we're going to use that for 8 years. So now y equals 4,000, 1.0025 to the 12 times 8, was that 96? Whew. So 1.0025 to the 96th power times by 4,000 gives us how much money? $5,083.47. Okay, and so that's our compound interest. And honestly, out of all of them, that seems like the most complicated. But the more you work through it, the easier it gets. Okay, so we've talked about exponential growth, and a special case of exponential growth was the compound interest. Now we're going to talk about exponential decay. So growth is when the quantity is increasing. Decay is when it is decreasing by the same rate. So for it to decrease by the same rate, what ends up happening in our exponential function is that we get our starting amount, and then we're going to do 1 minus the rate. So we're going to take the remaining percentage and times by that. So that's why we do the 1 minus. So decay we subtract, growth we add. And other than that, the formula is the same. So let's go ahead and look at our problem. The population of a town is decreasing. So here's a key word, exponential decay. We're decreasing at a rate of 3% a year. In 2000, there were 1,700 people. So y equals 1,700 people. We're going to do 1 minus our 3%, so 0.03 to the t power. So this becomes y equals 1,700 times 0.97 to the t power. And that's how we know it's decay, is when this number is less than 1. Because it's going to take off a little percentage each time. So now, if we want to find the population in 2012, we've got to figure out how much time. So from 2000 to 2012, our time was 12 years. So what's our new population? Well, y equals 1,700 times 0.97 to the 12th power. So now we calculate 0.97 to the 12th power, which is 0.6938, so on and so forth. And then I'm going to times that by the original population of 1,700. And that tells us that there is 1,179.53 people. But because we're talking about people, and we know this, we have to round appropriately. So really this is 11,080 people, because we would round up. Okay, next one. The fish population in a local stream is decreasing, so exponential decay, at a rate of 3% a year. The original population was 48,000. So original was 48,000. We're decreasing, so 1 minus that 3%. So there's our function. I'm going to go ahead and simplify that a little bit. 48,000 times 0.97 to the t power. And then we're going to find the population after 7 years. So we're going to do 48,000 times 0.97 to the 7th power. So 0.97 to the 7th power, which is 0.80798. And then we're going to times by the 48,000. And we get 38,783.17655. And again, we're talking about items that really doesn't make sense if we have decimals. So let's go ahead and round appropriately. So about 38,783 fish. And that's it. So exponential growth, compound interest, exponential decay, and then let's go ahead and look at half-lives. So here's another science thing having to do with exponential decay. So a half-life of a substance is the time it takes for one half of the substance to decay into another substance. So for half-life, the exponential growth function, well, a half-life function, wow, there's some typos in here. A half-life function has the form of A equals P, so our original amount, times 0.5, that's where we get the half-life, so we multiply by half to the t power. And t is the number of half-lives in a given period. So we have this thing, astatine 218 has a half-life of 2 seconds. Find the final amount left in a 500-gram sample of astatine 218 after 10 seconds. So we're going to go ahead and we're going to do y equals our original amount times half, and then we're going to do the number of half-lives in a given period. So if I have 10 seconds and my half-life is 2, then that's going to be 5. So if you ever get confused, you can think of number of half-lives in a given period. So it would say total time divided by half-life time. And that's what we're really doing, is figuring out how many times are we going to hit that half-life. So this now turns into 500 times 0.5 to the 5th power. So 0.5 to the 5th power. So this becomes 500 times 0.03125. Which means that really at the end we're going to have 15.625 grams of that left. And when we're weighing things, decimals are totally appropriate, so we don't round. Okay, next part. Find the amount left from a 500 gram sample after 1 minute. So again, using the same idea, we have a 500 gram sample, our half-life, so half, and then after 1 minute is really how many seconds? Well, that's 60 seconds. So we're going to take 60 seconds, divide it by our half-life of 2 seconds to get a power of 30. So this is now 500, and then we have our half-life to the 30th power. So we'll do 0.5 to the 30 power. Oops. And then I'm going to times that by 500. And it's going to tell me that I have, now my calculator does this, 4.6566 e negative 7. Which really means that this is times 10 to the negative 7th power, which means I move my decimal 7 spots forward. So it's really 0.12345 and then I hit my 46566. And so that's how much grams I have left of that substance. And that's how half-lives work. So let's look at our next one, our last one for today. Cesium-137 has a half-life of 30 years. Find the amount of cesium-137 left from a 100 milligram sample after 180 years. So y equals, I have a 100 milligram sample. I'm working on a half-life. And my total time is 180, and my half-life time is 30. So this becomes 100 times 0.5 to the, well, what's 180 divided by 30? Pretty sure it's 6. Yep, 6th power. So we're going to do 0.5 to the 6th power times 100, which tells me that now it's going to be 1.5625 milligrams of that substance after 180 years. And that's it for half-lives.